We can take some questions now, and then I'll give the first part of the lecture, then we can take a break, and then some more questions afterwards. So, anything you want. Any questions about machine learning?
Can we have general questions as well?
Yeah, you could have general questions, sure.
I'd like to ask the question, how does all these Bayesian stuff correspond with non-IID settlement?
So non-IID, yeah. Oops. I'll talk about that a little bit in this lecture. So I'm going to talk about data that is what's called exchangeable. I'm going to talk about data that is relational. I'm going to talk about hierarchies. And I'm going to talk about time series. And all of these are examples of non-IID data. Okay. So any other questions? I'll take 3 more and then...
Is it a problem if you want to use in Gaussian processes wavelets as kernels, but when we don't know the exact formula for wavelet?
When we don't know the exact formula for the wavelet. Yeah. Let me rephrase your question slightly. So what do we need to be able to run a Gaussian process?
We need only matrix.
We need a way to compute the kernel, right? So now if your kernel is based on a wavelet representation of your data, then you have to be able to compute the kernel, because if you can't compute the kernel, then you can't define the Gaussian process. So I don't know whether that answers your question, but the way you asked it, it suggests that the answer is no, that you can't use the model if you can't compute the wavelet representation in that wavelet basis. But maybe that's not a good answer. I'm not sure. Okay? Yeah?
How Gaussian processes deal with imbalanced data problem?
Imbalanced data, yeah, it's a very interesting question. Okay. So imbalanced data refers to a very common situation where you might have something like, if you're modeling, I don't know, patients, you might have 99% healthy patients and 1%, diseased patients, okay? For some rare disease, this is very normal situation that most of your cases are going to be, let's think of classification, most of your cases are going to be in the negative class, and a very small fraction are in the positive class. Now, in general, for probabilistic models, this is not usually a problem. So, you could imagine a situation where these are all your negative points, and you have a lot of negative points, and then you have a few positive points. Okay, this is maybe an imbalanced classification problem. So the correct classification here is anywhere you look with higher probability, it's healthy than it's more probable that it's healthy than diseased, right? The problem with imbalanced data is not the fact that the data is imbalanced. The problem is that your loss for misclassifying a diseased person as healthy is much higher than your loss for misclassifying a healthy person as diseased, okay? So if you're trying to do medical diagnosis, you have to care a lot about sending a patient home and saying you're fine if they actually have some very deadly disease, right? So the way Gaussian processes and other probabilistic models deal with imbalanced data is by taking the probabilities and then combining them with a loss matrix, which is supposed to represent the loss of getting wrong, getting false positives or false negatives. And then you combine the probabilities with the loss matrix, and then you come up with a decision that minimizes expected loss. Okay, this is the basic sort of idea behind decision theory. Okay, so it's okay if your probabilities say 99% healthy everywhere. Okay, as long as they say maybe here it's maybe in this region they're slightly higher to be diseased, and in the other regions they're slightly higher to be healthy. Okay, that's a fine classifier. Then you need to put that into a reasonable loss to make decisions. So you don't have to change Gaussian processes at all to deal with the imbalanced data.
But there are some techniques which modify the kernel function to deal with.
Yeah, maybe in SVMs, yeah, because SVMs, the difference between SVMs and Gaussian processes is that because SVMs are minimizing a sort of an objective function, they try to come up with one solution, right? And then maybe the solution that it comes up with is everybody healthy, okay, in this situation. And that's not a good solution. So you change your objective function to fix that in an SVM. In a Gaussian process, the output is a probability, okay? So if a Gaussian process is working okay, the output will be, here 99.5% healthy, here maybe 98 or 97% healthy. Okay, so those probabilities can then be used with a loss function to make decisions. So you don't have to modify the probabilistic prediction. Okay. It doesn't make sense. If I'm trying to predict what is the probability of snow tomorrow, okay, it's hopefully very low. Okay, but I shouldn't change that probability just because it's imbalanced data, right? That probability means something. Okay, I'll take one more question, and then I'll move to the lecture. Okay.
So I'm thinking of a specific use case, and I'm wondering which model would be the best for it. So a use case is that I want to have a social network, but not of people, but of some objects. These objects have some features which can be generally expressed as numbers.
Mm-hmm.
And now I would like to connect these objects in some relations, but I would like to make it more like Google Plus, meaning that's not friends, but it may be family.
Different kinds of relations.
So in general, this model can be expressed as a graph with some waves, but I wouldn't think of any directions rather not directed.
Mm-hmm.
But I'm quite uncertain which of the models you described during your lectures would be the best for it.
And none of them so far, no. So it's good that you're uncertain, because I don't think any of them is a good model for that particular situation. I'm going to talk about networks and relational data at the end. And I'll talk about specifically models of undirected networks. Maybe that will help. I'll give you examples of things, but for your particular use case, you probably have to modify some of the models I'm going to talk about. Right. Okay, so yeah, that's an interesting topic. All right. Okay, so let me just get started, and then after the break, we'll have a few more questions. Okay, so this last lecture is going to be really about topics that I'm actively very interested in terms of research. And that's in the area of Bayesian non-parametrics. And the first half before the break is going to be necessary background. And then the second half will be some recent research work that we've been doing. So this idea of Bayesian non-parametrics is, as I have described throughout, is kind of based on the idea that we're trying to do machine learning by building probabilistic models. And if we take the term Bayesian non-parametrics, obviously it has two parts to it. So let me explain the two words and why my research is largely focused on this area of Bayesian non-parametrics. So why Bayesian? Well, I've tried to give you quite a lot of motivation for it, but it comes down to simplicity, okay? It's just a very, it might feel complicated, it might be complicated to implement, but conceptually, it's very simple. It just says, use probability theory. In fact, we shouldn't even use the word Bayesian. Okay, it almost would be, I would be perfectly happy if we just called it probability theory. Okay? It's sort of like, if somebody who uses calculus would be called a Newtonian. Okay, it's a bit strange, right? Just say they use calculus. Okay, so we're going to use probabilities. Okay? But now why non-parametrics? Well, non-parametrics has to do with the fact that what we're trying to model is complicated. Data in the real world, like, networks or time series or hierarchies or even IID data, it tends not to come from simple models, okay? So we need our models to be flexible enough to handle the complexity of real-world data. So let me distinguish between parametric and non-parametric models. Parametric model assumes that you have some finite set of parameters. For example, linear regression or quadratic regression has some finite set of parameters. And given the parameters, any future predictions are independent of the observed data. So probability of some new data given the parameters and all of your training data is equal to the probability of the new data given the parameters. The parameters capture everything there is to know about your training data. Okay? You can think of the parameters as a summary of everything about your training data. Once you know the parameters, you can throw away your training data. Now, I like to think about these models from an information theoretic point of view. So one way to think about probabilistic modeling is as an information channel from past data to future predictions. Okay? It's like a communication channel. So a parametric model says that all the information from past data is summarized in this set of parameters, and that's all that's required to predict any future predictions. And if you have a parametric model, because you have a finite set of parameters, then this channel has a capacity that's bounded by those parameters. So no matter how much data you observe, the number of bits of information between past data and future predictions is going to be limited by those finite set of parameters. Another way to think about it is that the complexity of the model is bounded even if the amount of data is unbounded. And that makes them not very flexible. So again, in the case of linear regression, if my model is linear regression, even if I have 10 million data points, the best thing I can do is fit a good linear regression. Okay. Non-parametric models, in contrast, assume that the data distribution cannot be defined in terms of such a finite set of parameters. Actually, the term non-parametric is a bit confusing because it's not that non-parametric models don't have parameters. Non-parametric models are often so complicated they can't be represented in terms of the parameters. So another way to think about them is that often non-parametric models correspond to assuming some infinite dimensional parameter space theta. Okay? And so the parameter in a non-parametric model, if that makes sense, the parameter is this infinite dimensional theta, and we can often think about theta as a function. And we already saw an example of this, which was Gaussian processes. That's a very classic non-parametric model. Now, the reason people call it non-parametric is because you can't write down explicitly what the values of the parameters are, because it's this infinite dimensional object. So you have to do something different. Like in the Gaussian process, you can't write down explicitly what the function is because you never know what the function is. You have a distribution over functions, and you do manipulations in that using, properties of Gaussians. Now, in contrast to parametric models, here the amount of information that theta can capture about the data can grow as the amount of data grows. And this makes them more flexible. Okay. Now, in a sense, another way to think about non-parametric models is that we need to store an increasing amount of information about our data set in order to make predictions. Okay? So as you get more and more data, the model becomes more and more complicated. So just some further motivation for why we like to think about non-parametric models. I've tried to mention the idea of flexibility. So it's more flexible to assume Gaussian processes than, some finite order polynomial. It's more flexible to assume clustering model with infinitely many clusters than a clustering model with 6 clusters. Flexibility turns into better predictive performance. So in general, the predictions are more reasonable for non-parametric models because they don't make rigid assumptions. And from a subjective Bayesian point of view, it's more comfortable to use a non-parametric model because it's somewhat more realistic. For example, if I was, modeling some data and I used linear regression to model the data, as a subjective Bayesian, I would be very uncomfortable, right? I would be uncomfortable because I'm putting all my prior probability mass on linear regression models, but I might not really believe that linear regression is a good model for this data I'm trying to model. But if I use a Gaussian process, I'm more comfortable because I know that a Gaussian process has what's called good coverage. And coverage is an idea I'll try to illustrate here. Let's think about a very large space, which is, let's say, the space of all continuous functions. Okay? So this is a large space. All continuous functions. And now we can think of parts of this space. So, for example, these are maybe all linear functions, right? These are all quadratic functions, etc. These might be all functions modeled in terms of sinusoids, etc. Okay. Now, coverage is the idea that I'm putting a probability mass on this space such that I might not be putting probability density on all continuous functions, but there is some, for any true continuous function, I'm putting probability mass somewhere near that. So I can approximate any true continuous function arbitrarily well. Okay? So a Gaussian process has this property that, for any true function, if I pick a suitable epsilon ball around that true function in a suitable way, I'm putting some probability mass on that epsilon ball. Okay? It's a little bit like saying the rational numbers give you good coverage of the real numbers. Okay? Near any real number, there are enough rational numbers so that I can approximate that real number. In that sense, the Gaussian process is realistic because I'm going to be able to model, in the limit, I could model any continuous function arbitrarily closely. Are you happy with that idea? Okay. But I can't do that if I assume just linear or quadratic, or even a neural network with 10 neurons or something like that, right? Now, another argument for why Bayesian non-parametrics is a practical argument, which is if you look at the history of machine learning, almost all successful machine learning methods are essentially non-parametric. What I mean by that is that they might not call themselves non-parametric, but they're flexible enough to be able to model all sorts of complicated things. So things like kernel methods like SVMs and Gaussian processes are non-parametric if you use anything but linear or polynomial kernels. And if you use something that's called a characteristic kernel, like the Gaussian kernel in SVM, that's a non-parametric model. It maps the data to an infinite dimensional space. Deep networks or large neural networks are, technically speaking, they're parametric, but these models can have hundreds of thousands or millions of parameters. Essentially, they're non-parametric. Okay, they're essentially operating in the regime where they're so flexible they could approximate almost anything. And even simple stupid methods like k nearest neighbors is a very nice non-parametric model. Now, the footnote here is that there are different ways of measuring success, and the methods I'm talking about here have good performance, but another attribute of success is scalability. So there are also other successful methods that are just so scalable that Google can apply them to every document on the web or something like that. Things like logistic regression are very highly scalable, even if they're parametric. And obviously, those are successful as well. So Bayesian non-parametrics has many uses. And the best way to kind of navigate the literature in Bayesian non-parametrics is to try to understand what is a parametric analog and where it tends to be used. Okay? So here are some examples we've already observed. So I talked about polynomial regression. That's a parametric model. The non-parametric kind of model that can be used here is the Gaussian process. The application of that is function approximation. And you know, the underlying process, the underlying non-parametric object here, or stochastic process here, is a Gaussian process. Now, because non-parametric models involve infinite dimensional parameter spaces, this theta is infinite dimensional, you need to deal with probabilities on functions, probabilities on these infinite dimensional objects, and that's why the non-parametric literature ends up using a lot of things from stochastic process theory. Okay? Stochastic processes is just probability distributions, not on vectors, but on functions. Okay? So we need that to do Bayesian inference in these non-parametric models. So the process here is the Gaussian process. Logistic regression is a nice parametric model for classification. The non-parametric analog there is a Gaussian process classifier. The underlying process is also still a GP, and the application is classification. Mixture models and k-means clustering are clustering algorithms. The non-parametric analog of that is something called the Dirichlet process mixture, and I'll talk more about that in this lecture. So the underlying processes are the Dirichlet process and its associated Chinese restaurant process. I'll describe both of those very soon. Hidden Markov models are a nice model for time series. We developed something called the infinite hidden Markov model. The underlying process for that is the hierarchical Dirichlet process. Factor analysis, probabilistic PCA, probabilistic matrix factorization. These are models for hidden feature discovery in array data. And the non-parametric versions of that are infinite latent factor models, and the beta process and Indian buffet process are examples of processes underlying that. So this is just to give you in a table form just some of the most commonly used Bayesian non-parametric models. There are many, many other ones. That's what the ... means. And this list is somewhat biased towards things that are either popular in machine learning or things that, you know, I've been interested in over the years. Okay, so the kind of the grandfather and grandmother of most Bayesian non-parametric models are the Gaussian process and the Dirichlet process. Okay, these are processes that have been around for, in the case of the Gaussian process, in various forms for more than a century, probably longer. In the case of the Dirichlet process, since the 1970s. Now, it's nice to have the Gaussian process and the Dirichlet process on one slide because I want to kind of emphasize the conceptual similarity of these two things. We already know what Gaussian processes are from the last lecture. It's a distribution on functions that's analogous to thinking of the infinite dimensional limit of a multivariate Gaussian distribution. A Dirichlet process defines a distribution on distributions. Okay? Now that sounds weird, but it's a very simple idea. Instead of just having any real valued function, let's have functions that are non-negative and integrate up to 1. Okay? So that's just a distribution is a function that's non-negative and integrates to 1 or sums to 1. Okay? So now G is such a function. We say G is drawn from a Dirichlet process. And the Dirichlet process also has two parameters. One of them is the base measure. This is actually the mean. G0 is the mean of G. And alpha is called the concentration parameter that models the variance of G, so the inverse of the variance of G. Okay? So just like the Gaussian process, it has a mean and a variance. Okay? But the objects that it produces are not just any kind of real valued function. They are functions that are non-negative and they integrate to 1. Okay? Now, the easiest way to visualize the distribution is using something like a histogram. So imagine that the object generated from a Dirichlet process is a random histogram. Every time you draw from it, you get a different histogram. But of course, that histogram, I've binned the axis to be able to visualize the histogram. Okay. Now, the Dirichlet process is the infinite dimensional analog of the Dirichlet distribution, which is a distribution on non-negative vectors that sum to 1. So let me just review the Dirichlet distribution for you, and then I'll review what the Dirichlet process is. Then I'll talk about applications of that to clustering and other topics. Okay. So the Dirichlet distribution is a distribution on the k-dimensional probability simplex. So, for some finite k, let P be a k-dimensional vector such that all its elements are non-negative and that the sum of the elements is 1. The Dirichlet distribution defines the distribution on these vectors P. We can write it like this: Dirichlet alpha 1 through alpha k. These are the parameters of the Dirichlet. And then the term in green is just a normalizing constant for the Dirichlet in terms of gamma functions, which I've written the definition of the gamma function at the bottom of this slide. It's small enough that you don't have to read it. Okay. It's just a generalization of the factorial to the positive reals. Okay. And then the form of the Dirichlet is that it's a normalizing constant times the product over j equals 1 to big K of pj to the alpha j minus 1. Okay? Now, this is a distribution on vectors P. It has the property that the mean of that distribution is simply the alphas renormalized. Okay? So expected value of pj is alpha j over sum over k alpha k. Okay? The variance is just given by the sum of the alphas. Okay? It's related to the sum of the alphas. Now, I mentioned this sort of important role of conjugacy in Bayesian models. It turns out the Dirichlet is conjugate to the multinomial distribution. So what does that mean? That means if you have some discrete variable c, which is drawn from a multinomial distribution with parameter p, this vector p, that means you have a discrete variable where the probability of observing c equals some value j is just pj. Then the given c, the posterior over p, is also Dirichlet. So if the prior is Dirichlet and this likelihood is multinomial, then the posterior is also Dirichlet. And in fact, it's a very easy computation. The posterior over p given c equals j and alpha is Dirichlet with some parameters, call them alpha prime. And alpha prime, all that happened was that alpha prime is just the alphas that you had from the prior plus 1 for element j. So you add a count of 1 to element j if you observe c equals j. Okay? And all the other alphas stay the same. So now we have a quiz. Yep.
So in 3 structure, if they think this is where the distributions for the hyperparameters come from, right?
So where do the, sorry, what's the question?
In tree-structured stick breaking,
Yeah.
There were distributions given when resampling hyperparameters, and this is where it comes from, right?
Yeah, so in this case, we could think of the data as C, the parameters at P as P, and the hyperparameters as alpha. Okay, so here's a little graph. Alpha is a vector. From that, we generate P, and then maybe we observe data point C1, C2 through Cn. Okay, and in our work on tree-structured stick breaking that you're talking about, we basically try to define a hierarchical structure over this this whole model with the hyperparameters in there as well. But this is maybe a little too advanced to kind of talk about here. So here's the, now we're going to do a quiz. Okay, let's say C is an element of 1, 2, 3, and I have a Dirichlet prior parameter that is, these don't have to be counts, so they could be 0.1, 0.1, 0.1. So P is drawn from, the prior on P is Dirichlet alpha. And now I'm going to have a data set D, which is three observations of, or a few observations of C. And these observations are 1, 1, 1, 2, 3, 3. So now what I want to know is what is the probability distribution, what is the posterior probability of P given this data set D when the prior was alpha. Okay, so here's how we're going to do this. First of all, ask me any questions if this isn't clear. This is a data set, like here in this picture. This is a data set with n equals 1, 2, 3, 4, 5, 6 data points. And these data points are C1, C2, C3 to C6. 6 observations of the variable C. And the variable C came from, like here, it came from a multinomial distribution with parameter P. Okay? So Cn is drawn from a multinomial or discrete distribution with parameter P. Okay, here's how I want you to do this. Talk to the person sitting next to you for a couple of minutes and try to see if you can figure out what the answer is. Okay. The answer depends a little bit on what's on the slide. Okay. Okay. Raise your hand if you think you know the answer. Okay. Raise your hand if you are confused about the question. If you have a question about the question. It's like a distribution on a distribution. If you have a question about the question, raise your hand. Okay. So I want to hear from somebody who, yes?
Question, does alpha prime has the same amount of values, or it can have more values than the alpha?
So alpha prime will have the same number of values as alpha. Because alpha prime represents, so P, okay, just to add something, some information here, P is a vector in the three-dimensional simplex. I'm going to draw it like this. Okay, P is a vector in the three-dimensional simplex, meaning that P, P1, P2, P3 sum to 1. Okay, P1, P2, P3 represent the probabilities of observing C equals 1, C equals 2, and C equals 3. All right. Alpha 1, alpha 2, alpha 3 are hyperparameters controlling the distribution on P. Okay, so somebody who is not very sure but has a guess at what the answer is. What do you think the answer is? So you seemed a bit hesitant. So I want to hear not from people who are confident, but from people who are not very sure.
I'm thinking about the foundations of my calculus. So.
Okay. Anybody else wanted to try to answer? Okay. So what would it, yeah, so, okay. Maybe somebody on this side of the room, but not in the first two rows. Okay, I'm gonna get you to answer the question. What general distribution does this, what family of distributions does this belong to? Okay, hint. We'll look at the title of this slide. Okay, Dirichlet. So, so just to be clear, the prior on P was Dirichlet. The data, the observed data, was drawn from a multinomial distribution. Multinomial is conjugate to Dirichlet. So the posterior on P, given the data, is also Dirichlet. Okay, so the answer is Dirichlet, but it's Dirichlet with some parameters, some new parameters, right? It's not the same parameters as the prior because we observed some data. So the posterior is the prior times the likelihood. So what are the new parameters of the Dirichlet?
3.1, 1.1, 2.1.
Yeah. Okay. So alpha prime is 3.1, 1.1, 2.1. Do you want to explain why?
From the application of the conjugacy, we were given the side.
Yeah, so, okay. So the way we can think about it is, if I observe, if I observe the first data point, then I started with a Dirichlet, And the first data point came in category 1. So I add a 1 to the first element of alpha. Now I observe the second data point. I add another 1 to the first element of alpha. I observe the third data point. I add another 1. So I get 3.1. Then this adds 1 here, and these two add 2 here. Okay? It's just counting, all right? There's no, you don't, because of this Dirichlet conjugacy property, you don't have to do any integrals or anything. You just add up the counts. Okay. So that's the Dirichlet distribution. Here are some pictures of the Dirichlet distribution. These are examples of the Dirichlet distribution over some vector theta, which is the same as this p here, with parameters theta 1, theta 2, and theta 3. Okay, and because theta is a non-negative vector that sums to 1, I don't need to draw theta 3 because theta 3 equals 1 minus theta 1 minus theta 2. So I'm drawing these as heat maps in theta 1 by theta 2. The Dirichlet 1, 1, 1 distribution is what distribution? It's the uniform distribution. Okay? So it's a fancy way of thinking about the uniform distribution, and that's because it's a distribution of the form pj to the 1 minus 1. Okay? Pj to the 0 is a constant, so this distribution is just not a function of p, or in this case theta, these parameters here. So the Dirichlet 1, 1, 1 is a uniform. The Dirichlet 2, 2, 2 put some mass on the center here. The Dirichlet 10, 10, 10 puts a lot of mass around what's the location of this point in theta space? Somebody tell me the location of this point here.
Center of the mass?
Yeah, the center of the mass is at what value here of theta? 1/3. So this location of this point is 1/3, 1/3, 1/3. The Dirichlet 10, 10, 10 has mean 1/3, 1/3, 1/3, and high concentration around that mean. The uniform distribution has mean 1/3, 1/3, 1/3, but very low concentration around the mean. The Dirichlet 1000, 1000, 1000 would look almost like a delta function around 1/3, 1/3, 1/3. Okay? And here are some other choices. The Dirichlet 2, 10, 2 has mean, close to this top corner here of the triangle. Triangle represents, remember, theta 1 by theta 2. So the Dirichlet 2, 10, 2 puts a lot of mass here, whereas the Dirichlet 2, 2, 10 puts a lot of mass here. Okay? And here's the Dirichlet 0.9, 0.9, 0.9, which puts more mass on the corners than in the middle. But the mean here is still 1/3, 1/3, 1/3. Okay. So these are just some pictures of the Dirichlet distribution. So now we move to the fun part. Okay. We've talked about the Dirichlet distribution. This is a distribution on these finite dimensional vectors. So let's talk about the Dirichlet process. So the Dirichlet process is going to be a generalization of the Dirichlet distribution to kind of any space. Okay, even not a finite dimensional, it's going to be a distribution on measures on any space. Okay, so let theta be a measurable space. Let G0 be a probability measure on theta. By probability measure, all I mean is, a non-negative function that integrates up to 1. Okay, think of it as a probability distribution, kind of informally. Let alpha be some positive real number. Now, for all ways of partitioning up this space big theta, G is drawn from a Dirichlet process with mean G0 and concentration alpha means that the amount of mass that G gives to any of those chunks A1 through AK, if I put those amounts of mass together, then this is what is this? This is a k-dimensional vector, right? The amount of probability mass or measure given to any of these sets is a non-negative number. And if this was a partition of the whole space, then the sum of these non-negative numbers is 1. So this is a k-dimensional vector, which is non-negative and sums to 1. And that k-dimensional vector has a Dirichlet distribution with parameters alpha, the amount of mass G0 assigns to A1, dot, 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 to alpha, the amount of mass G0 assigns to AK. Okay. So let me explain that a little bit more with this picture. So G0, what is this object G0? It's going to be a measure on theta. So just think of it as a probability distribution over theta. So for now, I've drawn something that looks a bit like a Gaussian, but it could be anything. Okay, it doesn't have to look like a Gaussian. It could be anything here. Any probability distribution on theta. So now we have this continuous space theta. What we're going to do is we're going to divide it up into chunks. Okay, can you see this well, or should I try to zoom in on it a little bit? Is that better? Maybe. Okay. So we have some base measure here on theta. And now I just arbitrarily choose to partition theta into, let's say, 1, 2, 3, 4, 5, 6 chunks, such that this is a partition of theta, which means that these sets are mutually exclusive and exhaustive. Okay, they cover the whole range. Now, I could do this in many ways. I could partition it into 10 chunks, or I could divide it into non-contiguous chunks. So for example, I could say this is A1 and this is A2. So I partition it into 2 chunks that are not contiguous. It doesn't matter. The point of the Dirichlet process is for any way of partitioning up this space theta, I have to now be able to look at the amount of mass that the base measure G0 assigns to each of my partitions. That's this G0, for example, here, the amount of mass under the curve here is G0 of A4, right? That's a number between 0 and 1. And then G of A4, this sort of, when I draw from my Dirichlet distribution, I start with a mean G0 and I draw a probability vector G. G is some measure on theta, some probability distribution on theta. The amount of mass that G assigns to A4, the mean of that is G0 of A4. Okay? Now, in fact, more than just saying that the mean of G is G0, the whole vector here, the 6-dimensional vector, which is G of A1, G of A2, G of A3, G of A4, G of A5, G of A6, that 6-dimensional vector has a Dirichlet distribution with parameters given by the G assigned to each of these sets multiplied by alpha, this concentration parameter. So when alpha is very high, then G concentrates on G0, which means when alpha is very high, it's a bit like this situation where the vector concentrates a lot around its mean. When alpha is low, then there is a lot of variability around the mean. So just to be clear, what is the picture that I'm showing here? The picture that I'm showing here is meant to be a representation of one sample from the Dirichlet process. Okay? But just like in the Gaussian process, I could draw many samples from this Dirichlet process. All right? And if I draw many, many samples, then I can compute the mean of those samples, and I would find that the mean looks like G0. And the variability in the masses assigned is controlled by alpha. Okay. So do you have questions about this? I'd like to recommend, I'm not going to go through it in this lecture, but there's some nice demos that Yi Tay and Peter Orbans developed for they gave a NIPS tutorial on Bayesian non-parametrics a couple of years ago, and they had some nice demos of drawing from the Dirichlet process. Okay. So this is the Dirichlet process. There are many ways of thinking about the Dirichlet process. It's an infinite dimensional generalization of the Dirichlet distribution because I could divide up theta into infinitely many infinitesimal chunks, okay? And this result would still hold, right? So in the limit where each of these chunks is getting, each of these A's is getting smaller and smaller, then this is still holding, right? So in the same sense that a Gaussian process, when you evaluate it at some finite number of points, is a Gaussian distribution, the Dirichlet process, when you evaluate it at any finite partition of the theta space, is a Dirichlet distribution. Okay. Okay, so that's the definition, but what does it look like? Does it look like something like this? If I drew a random draw from this, does it look like something like this? Well, it turns out it doesn't really look like something like that. A sample from a Dirichlet process is going to be discrete with probability 1. In other words, even if my base measure, G0, is this nice continuous thing, when I draw a sample from, when I draw a sample G from a Dirichlet process with mean G0, the sample G is going to look something like this, where these spikes are meant to represent delta functions now. So, sorry, it doesn't look like this thing integrates to 1 if that thing integrates to 1. But what I mean by these spikes is really delta functions of certain heights, okay, Dirac delta functions. So we can represent a draw from a Dirichlet process by an infinite sum of weights. These are these pi k's at different locations theta k. So theta k represents the location in theta, and pi k represents the height of this Dirac delta function, the sort of mass of that Dirac delta function. Now, the expected value of this thing g is going to be g0. So on average, the amount of mass assigned to any region in theta is going to be the same for g than for g0. But any particular sample will look very different from g0. And as alpha goes to infinity, g looks more and more like g0 in that, if I were to take a histogram of g and I to take a histogram of g0, then these two histograms would converge to each other. Okay. Okay, sorry, this is because I built this format. Okay, so now Dirichlet processes have been used for clustering. Let me describe to you the application of Dirichlet processes to clustering. And in the machine learning community, this is often called infinite mixture models. It's a nice way to think about it. So the other name for it would be a Dirichlet process mixture. If you take the standard clustering model, like a Gaussian mixture model, and now you ask yourself, is there an analogous model which contains countably infinitely many Gaussians? What would that be? Well, that's an infinite mixture model or a Dirichlet process mixture. But it's not just a mathematical exercise. Let's think about why we would want to do this. Okay, so the reason why we might want to do this is because we might not believe a priori that your data comes from some finite number of components. Just like you might not believe that your phenomenon is well modeled by quadratic, you might not believe that a mixture of 6 Gaussians is a good model for your data. Now, inflexible models in general can yield unreasonable predictions. So we want models that are more flexible. And in many applications, actually, the number of clusters grows naturally over time. So for example, if I'm trying to cluster news stories or emails or spams or classes of visual objects or something like that, I imagine that the more data I get, the more clusters I will observe in the data. Okay? And what we'd really like are methods that automatically infer the number of clusters in the data. So here is one way of representing a Dirichlet process mixture of Gaussians. And then in a minute, I'll describe what the actual generative model is. The idea is a good way to understand the model is to think about data that the model would generate. Okay? So here, I'm showing you data that a model would generate in 2 dimensions, where the model is an infinite mixture of Gaussians. So these are 10 data points. And you can see that there's some clustering in the data, maybe. If I draw 10 more data points, you see more clearly that there's some clusters. These are 80 more data points, so a total of 100 data points. And these clusters are coming out quite cleanly. And this is a total of 300 data points. And you can clearly see, a bunch of nicely separated clusters. Okay? So what is the point of this? The point of this is in a model like this, the more data you have, the more fine structure you observe in the data. Okay? The more data you have, the more new clusters you expect to observe. If you're clustering news stories on the web, that's a bit like saying, if I take 100 news stories, maybe I observe a few different kinds of news stories. If I take 1 million news stories, I will have lots and lots of different kinds of news stories. So I need more and more clusters for that. Now, how do we generate infinite mixture models? Well, one way of doing that is you take a finite mixture model and you consider what happens in the limit when the number of clusters or components goes to infinity. So here is a description of a finite mixture model as a probability distribution. The pi's represent the fraction of data captured by each cluster. And pk of x represents the probability density for the kth cluster. So we start with a finite mixture model, and we take the limit as the number of components goes to infinity. But of course, now we have infinitely many parameters. Like, if we had 6 Gaussians, now we have infinitely many Gaussians. So we can't obviously fit them to data. We can't do optimization because we would overfit. But instead, you can integrate them out. You can marginalize them out, all the parameters of all the clusters. And so this is just where different approximate inference methods can be used. So again, remember the distinction between a model. We can write it like this. This is the finite model. Then we take the infinite limit. That's the infinite mixture model. And now we can consider different methods that could be applied to learning in these models. And just historically, most of these methods are based on Markov chain Monte Carlo. In statistics, this is very, very heavily used, these kind of Dirichlet process mixtures. And there are many, many references, much more than I can fit on this slide, for different MCMC algorithms for doing inference in these models. Just a sort of interesting contrast to Gaussian processes. In Gaussian processes, expectation propagation seems to be the best way of doing classification. Tom Minka and I tried to develop an expectation propagation algorithm for infinite mixture models, and it was much worse than MCMC. So this is an unpublished technical report where we describe our attempt at doing EP for this model, and we show that it's actually a worse speed accuracy trade-off than doing MCMC.
Question?
Yep.
In this case, would you advise MCMC for clustering? Or one of the later?
So other options are variational methods. There's a nice paper by Bly and Jordan which applies variational methods to these infinite mixture models. That seems to work reasonably well. And then we also have a deterministic single-pass hierarchical clustering algorithm that, that works even better than variational methods for this model. But it's not very widely used. It's reasonably used. But most people in statistics use MCMC. What would I advise is the question. I would not advise EP. We know we tried it. It doesn't work very well. Any of the other three is very reasonable, depending on whether you want to wait a long time and get a very good answer, or you want to wait a little time and get a quick answer. So these methods are probably the quickest, the Bayesian hierarchical clustering method. Okay? Now, just like the Dirichlet distribution had some conjugacy properties, the Dirichlet process has some conjugacy properties. So if the prior on G is a Dirichlet process, I'm going to write it like this. And if you observe a value of theta, so probability of theta given G is just G of theta, which is kind of exactly analogous to what's happening here for the Dirichlet distribution, then the posterior on G is also a Dirichlet process. So this is very loose, if kind of a very careful statistician would not like my notation here. It's a bit loose, okay? But I'm just writing Bayes' rule to give you the idea of what's happening. I have a Dirichlet process prior on G. I have a likelihood on G, which says that the probability of theta given G is just G of theta, which is the same situation as here. The probability of C given, the probability that C equals J given P is just P sub J. Okay. Then the posterior on G given theta is a Dirichlet process with an update to G0 and an update to alpha. So G0 is updated by adding a delta function at location theta and then renormalizing. Alpha is updated by adding 1 because we have one extra observation here. And a generalization for n observations looks like this. So this is alpha is updated with n observations and G0 is updated with n delta functions and then renormalized. Okay. So I'm just giving you these results, but they're completely analogous to the results on conjugacy for the Dirichlet distribution. Okay. Now, there is an urn representation for Dirichlet processes. I'm not going to go through the equations in great detail, but the basic idea is that is the following. And let me just go through this equation without proving it to you and just give you the intuition for what is happening here. So this equation is saying what is the prediction for theta n given the observations of theta 1 through theta n minus 1. Theta is just some observation in this space, big theta. Okay? So what is the prediction for theta n given observations theta 1 through theta n minus 1 when my prior was a Dirichlet process with mean G0 and concentration alpha? And the prediction is with some probability proportional to alpha over n minus 1 plus alpha. I'm going to get that theta n is drawn from my base measure G0. And then with some probabilities proportional to 1 over n minus 1 plus alpha, I'm going to get that theta is equal to one of my previous thetas. Okay? So this is a kind of clustering effect that comes from the Dirichlet process. And essentially what it means is that if I were to sample from my Dirichlet process, I would get repeated values of thetas. And that's pretty clear, that's pretty clear from this picture here. If I were to sample from this distribution, right, then I'm going to, after a bunch of samples, I'm going to get repetitions of exactly the same value multiple times. Okay? So the thetas are going to be clustered because it's a discrete distribution. So this is why this funny object, the Dirichlet process, is used in clustering. Okay? Because it exhibits a particular clustering effect because the distributions you get are discrete. So just to kind of clarify some of the relationships, the Dirichlet process is a distribution on distributions, or some people might call it a measure on measures. Okay, distribution on distributions. Now, this results in discrete distributions. The draws from a Dirichlet process are discrete. So if you draw endpoints, you're likely to get repeated values. What that means is the Dirichlet process induces a partitioning of the endpoints. So imagine I drew n thetas from the Dirichlet process, and I observed that theta 1 and theta 2 are different, but theta 3 is equal to theta 1, and theta 4 is equal to theta 3, and theta 5 is equal to theta 2. This is a possible scenario when I draw from any distribution with a bunch of delta functions. So what that corresponds to is a partition on the integers 1 through n. So this corresponds to the partition 1, 3, 4 are in one group, and 2 and 5 are in a different group. Okay? This is like a clustering of n data points. Now, the distribution on these partitions is a discrete object. The Dirichlet process is a continuous object. It is basically, sorry, it's it's a measure. You could think of it as a stochastic process. It lives on some continuous space theta, etc. The Chinese restaurant process is the corresponding distribution on partitions. It's a combinatorial object. It just counts how many times certain objects are in the same subset of the partition. Okay? So that's the Chinese restaurant process. I'll describe that in the next slide in a little more detail. The Chinese restaurant process defines the corresponding distribution on partitions. And although the Chinese restaurant process is going to be described in the next slide as a sequential process, the distribution on these thetas is exchangeable. It's invariant to permuting the indices of the thetas. Okay. So here is the Chinese restaurant process. Chinese restaurant process generates samples from the distribution on partitions induced by the Dirichlet process mixture. The way we think about it is, this is an analogy that people like Aldous and Pittman came up with many years ago. We think about it as a process where customers enter a Chinese restaurant, and the restaurant has infinitely many tables. It's a very big Chinese restaurant, and each table is infinitely big. Okay, they are based in Berkeley, California, and there are lots of Chinese restaurants there that are very big. Right? The ones in London are much smaller. They don't fit big tables in them. But imagine an infinitely big restaurant with infinitely many tables. So here's how you generate a partition of the integers from the Chinese restaurant process. Customer 1 enters the restaurant, and without loss of generality, we say that he sits at table 1. Okay? So customer 1 sits at table 1. Then we initialize k is the number of tables currently, n is the number of customers currently, n1 is the number of customers at table 1, and that equals 1. Okay? So now for all subsequent customers, customer little n sits at table k with probability proportional to the number of previous customers at table k. For all of the existing tables, or all the tables that have people at them, customer n sits at table k plus 1 with probability proportional to alpha. So alpha over this total number, so that these probabilities all sum to 1. Okay? So that's sitting at a new table. So in this example, obviously if a new table was chosen, then we need to increment the number of tables, and obviously we need to increment these counts as well. So in this example, customer 1 sat at table 1. Customer 2 chose the second path and sat at a new table. Customer 3 then could sit at either table 1, table 2, or table 3 and chose to sit at table 1. Customer 4 then chose to sit at table 3, etc. Okay? So after n customers enter the restaurant, what you get is a partition of the integers 1 through n, where that partition involves grouping the groupings around the different tables. Everybody happy with that? Now, one interesting property of the Chinese restaurant process is that it has this rich get richer property, which means a popular table is going to get more people coming to it, more and more people coming to it. But it doesn't diverge. You know, you still get new tables appearing over time. All right. So here is a big picture on the Chinese restaurant process. there are many ways to derive a Dirichlet process. Sorry, this is a big picture on the Dirichlet process. We could start with the Dirichlet distribution and take the infinite limit. There is the Blackwell-McQueen-Ern model, which I didn't really talk about very much. There is the Chinese restaurant process view of the Dirichlet process that just looks at the clustering. There is something called a Styk breaking representation, which I also didn't talk about, but it's very interesting. It's another way of deriving this. And finally, I'll explain this one because it's very simple, and I quite like this representation. Here's one way of generating from a Dirichlet distribution. Let's say I want to draw P from some Dirichlet with parameters alpha. So how do I generate those on a computer? What is a way of generating a Dirichlet distribution on a computer? Don't worry about the Dirichlet process. We're just going to generate from the Dirichlet distribution. So here's a very nice way I can do that. So let's say P is in the k-dimensional simplex. Okay, a k-dimensional vector that sums to 1. So the way we're going to do that is we're going to draw a bunch of variables gi independently from gamma distributions. So the gamma distribution looks sort of like this. It's on the non-negatives. The exponential is a special case of the gamma distribution. It's very easy to draw independent gamma random variables. And then I just say Pi is gi over sum over j goes from 1 to k of g j. I normalize. So step 1, draw a bunch of independent gamma random variables. Step 2, normalize them. Now I have an object where all the elements are non-negative. They all sum to 1, and they're drawn from a Dirichlet distribution. Okay? So that's one way of drawing from a Dirichlet distribution. The Dirichlet process, you can also draw from it that way, except you draw a gamma process, and then you normalize it, and then you get a Dirichlet process. So that's another very elegant way of thinking about the Dirichlet distribution or Dirichlet process. Now, a Dirichlet process mixture is a way of just using the Dirichlet process on the parameters of a mixture model to come up with a model for clustering. It's a mixture model with infinitely many components where the parameters of each component are drawn from a Dirichlet process. And it's useful for clustering. Assignment of points to clusters follows a Chinese restaurant process under the prior. Of course, that's under the prior. When you observe the data, then the assignment follows whatever the posterior is. Okay. I think we could take maybe a break now. Let's take a 15-minute break.